All right, good afternoon, folks. Today is our sort of first real use of Unity. And C# sort of with Unity is a very big topic. There's sort of lots of extra stuff that Unity adds in for for using the engine through C#. So obviously we can't really go through all of it, but I want to show you some of the important pieces. And then as we need other things while we're working on games, we will sort of use those. I'll introduce them and all that kind of stuff. So today is just really sort of a basic usage of how we can actually turn some of the code that we write into some action happening in our game when it is running. That's sort of the main thing today. Plus, there'll be a little physics lesson and stuff that that we'll have as well. So let's get started. So when you create a new script in Unity, and we saw this last time before we messed around with sort of regular C# stuff, you get something that looks like this. And let me turn on my my little highlighted pen here. There we go. All right, so you get something that looks like this, and the sort of top sort of using stuff here is equivalent to the imports that you would see in Java. So Unity Engine, of course, includes a ton of stuff. System.collections, and then of course .generic. These are sort of more C# stuff rather than Unity specific stuff. We'll add some more usings in later on. So there's like Unity Engine.ui, for instance, when we want to do some UI stuff. So there are more that we can add in, but at a fundamental level, you'll typically need the Unity engine at the very least. And then if you end up needing to use some lists and stuff like that, some collections, similar to linked lists and array lists and stuff in Java, then you'll have these. You'll want to make sure that you're using these as well. I typically just keep them in there unless I specifically know that I'm not going to use them, in which case I'll remove them. But typically, you should just leave these in. It'll create the class for you that inherits from MonoBehavior. Like we saw last time, if you just want to make a straight up C# class, you can get rid of the extends MonoBehavior part here, so the colon and the MonoBehavior class. It also gives you start and update. One of the things that you might notice here is that they don't use that override keyword. I mentioned last time that if you're overriding something from a base class, you have to have override. This is because MonoBehavior does something very different. There is no start or update in MonoBehavior. There is no sort of start or update or any of the other sort of functions. It does a different process. And it's not something that I'm as used to using, but it sort of does things where, at sort of a top level view, it looks in your class and it sees, is there a start function? And if there is, it will run it. And it looks in your class and looks at, is there an update function? And then if there is, it will run it. There are a bunch of functions that behave this way. And so when you see things like on collision enter or on trigger enter or a fixed update or any awake, any of a myriad of number of these functions, they are functions that MonoBehavior is going to end up looking for, but not that are directly overridden. So if you're kind of wondering, well, how does it run if this isn't overridden from like MonoBehavior or something? There is some other special stuff that goes on in the background. Any class that you want to add to a game object. Remember we took our script and we dragged it onto a game object. Any script that you want to add to a game object must inherit from MonoBehavior. That's a requirement. So if you take this off, you essentially are informing yourself as you code it that you will not be adding this to a game object. You cannot do that. Start runs when the object is created. This can be either created when the game starts or when you instantiate an object. And we'll talk more about sort of instantiation and all that stuff later on. But start is sort of the first thing that runs. There is another function called awake that can run beforehand, but we'll talk about those later on. Update runs every frame. And all of that, you can think of it as being part of MonoBehavior, although there's sort of some technical stuff in the background that I mentioned earlier. So start and update are what's sort of given to you right away. Start runs essentially the first frame, or there's as soon as the object is created, and update is run every single frame. You can always make regular classes too. That's what we did last time. So you do not have to inherit from monobehavior. If your class is a child class of something that inherits from monobehavior, then that relationship is still there. So if I make a class, so I have this my class. If I make something that inherits from my class, then that thing is also a monobehavior. So you can do some inheritance structure with classes that you put onto objects, because they would all be monobehaviors if the base class is also a monobehavior. All right, so if every script that you attach to a game object is a component of that object. Unity follows this component-based system. When you drag a script, it's a component. You have access to information about that object via this. So you will see me use sort of this in various places. And it can access other components attached to the object as well. So if you have multiple components, say you have your script that you added on, and you have a transform, which is automatic, and you have a rigid body, and you have another script that you added to a game object, you can access all of those. So if you need to call functions, if you need to access data, you can do so on a single game object. There's lots of little quirks when it comes to accessing and changing other components of a game object. We're going to code something like this up, but not at this very moment. But I wanted to point out something here, where I'm grabbing this transform.position, saving it into a position variable, this pos variable, and then I'm changing the value of the x component, and I'm saving it back. Now, you might think, all right, he did this in 3 lines. Couldn't you just say this.transform.position.x plus equals 0.5? Why is it sort of this 3 lines? Why can't you do this in 1 line? There's restrictions to modifying individual components directly of the transform. So there's a bunch of these little quirks. That's sort of what I want to point out here. There's a little quirks that Unity restricts you from doing certain things. And so something that would normally take maybe 1 line to do takes 3 lines. These are things you have to get used to. These are things where you'll try to do something, and then you'll get some sort of error, and you'll be like, what in the world's going on? And you'll look it up, and you'll be like, oh, the standard way is this, because Unity says you can't do it that way. So there are little quirks, just like sort of any language or any sort of a library that you're using. Engines do the same sort of thing. There are little quirks that they sort of don't allow you to do for whatever reasons that the programmers or the designers decided. So in this case, we grab the full position, update the x value, and save it back. And you have to do those 3 steps. And so we will be doing that a little bit later. Unity has some important classes that you're going to see all the time. So things like, and I have a link here that is part of the manual that's like scripting important classes. So it's going to have a list of a bunch of them. A few of the highlights here are monobehavior. Of course, we have to inherit from monobehavior if we want to be able to attach our scripts to game objects. Transform is another class that is automatically part of any game object. It contains the game object's position, rotation, and scale. And we'll take a look at that in the inspector in just a little bit. And some other important ones that we'll use later on, not so much today, but a bit later on, are rigid body and its 2D variant, rigid body 2D. If you have to have a rigid body on your game object in order to interact with the Unity physics engine. So there's lots of useful classes. We're going to look at the vector class here in just a second as well, but these are quite common. You're going to be using the transform a lot. You're going to be using rigid bodies. The next one, the vector classes, you're going to be using those as well. But there are a lot of them. There are a lot of nice, useful classes that Unity gives you to help out. But these are definitely some of the highlights here. All right. The vector classes are very common as well. So there's vector 4, vector 3, vector 2. There's probably a vector 1 because you can set stuff. You can create vector 1s in certain aspects. I've never used a vector 1, but they're Unity's representations of vectors and or points. So think of like a point in space. So if you make a vector 3, you would say something like vector 3, here's a vector 3 pos equals new vector 3, and then you give it 3 arguments for the x, the y, and the z position, if you want to think of it as a point in space. So you're going to use these vectors or the vector-like objects to describe the positional, the rotational, the scale information about your game objects. So if you want to move a game object, typically you'll be doing something with a vector. Or if you want to figure out what's the distance between 2 points, maybe you have a player and an enemy. What's the distance between them? You're going to need a vector to represent that. So linear algebra in this sense, plays a huge part in any game. Luckily, because we're using an engine, most of it's behind the scenes. We won't have to worry about using rotation matrices to rotate the vertices of our 3D model. We don't have to worry about that stuff. Unity takes care of that for us. But there will be times when we have to do our own vector or matrix operations. And I'm going to show you a couple of those today and sort of give you sort of an idea of how vectors play a role in what we're going to end up doing for pretty much all the games in this class. We're going to be doing things with vectors. If we want an enemy to chase the human player, we need to know which direction the enemy needs to move. And so we'll be doing some calculations with vectors. So there's two ways to think of these vector objects: as points in space or as an arrow with a magnitude and a direction. So if you want to think of them just sort of purely as points, let's say we had 2 points, just 2 vector 3s. I just picked some values here. It's not really important what they are, but you can do all the normal calculations with them. You can add 2 vectors. And so you just literally just add the components. So 1 plus 0, 3 plus 5 to 8, 5 plus 0 to 5. Subtraction, right? We just subtract them. Scalar multiplication. I can just multiply 3 by whatever vector, and I get all the components multiplied by 3. Same thing for division as well. So if you have a vector 3, you can do all of these operations, and it would work how you would expect. The more sort of useful way to think about vectors is as arrows. So if you've taken a physics class, whether that was in high school or whether it was here at Wentworth, vector addition and vector subtraction are very, very important. Understanding what they mean in terms of vectors as arrows. And it can be useful to draw out the arrows on a piece of paper. I have a project where you have sort of a swinging ball and stuff, and I had to figure out various velocity vectors and acceleration and the sort of pendulum motion type stuff that I was coding. And I pulled out a piece of paper and I was drawing out all the vectors to make sure that I understood how all of this was working and what I needed to do, vector wise in order to get the forces to all work out. So let's say we have those 2 vectors again. If you add them together, the picture of that would look like this. And this is probably something that at least hopefully you've seen before. This is relatively common, where you sort of take the first arrow and then you connect the other arrow to the head, and then you draw the sort of resultant line. So if you add 2 vectors together, this would be the resultant vector. You can also do the parallelogram method as well. When you subtract 2 vectors, you would take that first, you would take so in this case, if we have V2 minus V1, it's the same as adding a V1 that's in the negative direction. So you can still do your parallelogram, or you can still do your sort of head to tail thing. And so you get a vector that looks like this. Now, at this point, you might wonder, all right, why is he showing us this vector stuff? Being able to have 2 vectors like this, you're going to have, one of these might represent the position of a player, and one of them might represent the position of, say, an enemy. The subtraction of 2 vectors is able to actually do a lot of work for us. It's actually able to help us quite a bit to figure out the direction that the enemy is from the player, the distance that the enemy is from the player. Those are very important concepts when you're programming a game. How far away something is from something else, and the direction that it is from something else. So I'm going to show you that right now. Let's say we had a target and a player. If you want to know the heading, in other words, if you want to know the direction, I would say the heading, I guess just think of the heading as the full vector, which includes the distance and the direction to the target. So now, in other words, the vector between the player and the target, you would take the target position minus the player position. The resulting vector 3 is this red line. So we have some reference point. Typically, the reference would just be 0, 0, 0. That's just a reference point typically. And then if you had a player here and a target here, that's your heading. The distance is the magnitude, the length of that vector. So you take your vector divided by the vector dot magnitude. That gives you the distance. And the direction, you would compute a normalized vector, which just has a length of 1. That's all a normalized vector is. There is a function for doing normalized. You could say heading.normalize, but all that means is it's dividing by the length. So you take the vector, divide by its length, then you get a single unit vector, and it's pointing in the direction of the target. So this is a common problem when you're working on a video game. How far is the target from the player and in what direction? And we will be using that specifically sort of mostly in our last game, where we had enemies that are coming in and trying to chase you and stuff. We will be using this in our AI calculations, because the AI is going to know where the player is. It knows where it is. It knows what direction it has to move, and in principle, how fast it can move as well. So these sorts of vector ideas do play a big part when you're working on creating any sort of game. So keep that in mind, sort of as we go along. You can also compute normal vectors. These can be very useful as well. For example, if you want to make sure that let's say you have a vehicle or something, and you want to make sure that it is at the right angle on an incline. Say you have some terrain, you're going up a mountain or something. The normal vector is sort of points completely perpendicular to the surface. And so oftentimes, if you want to make sure you're at the right angle based on the terrain, you have to compute the normal vector, which if you have 2 vectors representing the surface, it's just doing the cross product. And then you can get the magnitude, and you can turn it into a unit vector. They're oftentimes mostly used in like computer graphics type stuff, and sometimes in 3D pathfinding, and also, like I mentioned, keeping your orientation correct on like a slope or something. So if you haven't messed around with like normal vectors before and anything like this, that's fine. We're not necessarily going to be having to use a bunch of this stuff as we're working on our games, but these are where vectors are very important. So the purpose of me sort of talking about this stuff isn't for you to remember all the math behind these things, to say that, oh, I need a normal vector, so I need to do a cross product. You don't necessarily need to remember that. You don't need to remember the use cases for these. I'm going to show you some of the built-in capabilities that Unity has, so that we don't have to reinvent the wheel when we're working with vectors. But hopefully this sort of shows that understanding some of the math and some of the interpretation behind these concepts is just as important as remembering the syntax. Because sometimes it's easy to remember, oh, I need a vector 3. But then you have to remember, what do I need to do with this vector 3 to have it point from the player to the target, or the other way around. So Unity has lots of useful classes like this that you can then take and do with what you need to do. Take a vector 3 or a vector 2 and do the calculations you need to do. Do a dot product, do a cross product to get the information that you need to get. So we will be using vectors. You're going to see them all the time. And for the most part, I'll try to sort of point things out and maybe have some pictures on the slides and stuff, so that conceptually it makes sense. But if you see folks online using particular types of code and doing things with vectors, try to think about what the vectors mean in the context of the code that they're writing. All right, so we're going to go back to some simple scripts. So I have Unity open. And it's just basically on a sort of a blank blank project. It's the same project that I was using before, but I just made a new blank scene. And I don't have any scripts in here. So I deleted the other scripts. So we're going to need them. So what I'm going to do first is I'm going to create a script. And it'll just be the script that we'll sort of mess with today. And I'm going to create a game object and a cube and stuff like that. So first, I'm going to make the script. So I'm going to say create C# script. And I'm just going to name it the same thing that we had before. Actually, maybe what I want to name it. Maybe I'm going to name it like mover or something. It doesn't really matter. Eventually, we're going to have this move the cube. But you can, in principle, name it whatever you want. Then I'm going to create an empty. So if I right-click in the hierarchy, I can say create empty. And it just creates a game object that doesn't represent anything. There's nothing there. The only component that it has is a transform. My transform, for whatever reason, when I created it, it's not centered at 0. So I'm going to make sure that the position here is all centered to 0. So position, I made sure it was all 0, 0, 0. The rotation is all zeros, and the scale is all ones. And we can name this whatever you want to. You can click up here and you can name it whatever you want. I'll just leave it as game object, but if it has a particular purpose, if it's supposed to represent the player, then you could rename it to player, for instance. The next thing I'm going to do is I'm going to right click in the hierarchy and I'm going to create a 3D object, a cube. And I'm going to zero this one out as well. For some reason, my stuff doesn't always put this at 0. So I'm going to zero it out as well. Notice it has more components. It has a transform, of course. It has a cube, a mesh renderer, and a box collider. So all of this stuff, because it is a cube, it has to have all these other pieces to it. So things like, what's the material? What is it made of? So how should it look when it renders? Stuff like that. We're not going to mess with any of this. But what I am going to do is in the hierarchy, I'm going to take the cube and I'm going to drag it onto the game object. So it becomes a child. So you can see that relationship there. So this is some setup for some of the movement stuff that we're going to do a little bit later on. So I have this cube. It's a child of the game object. And if you have any questions, if you want me to repeat something or sort of show again sort of where I'm clicking and what I'm clicking on, definitely let me know. Throw it up in chat or say something over the mic. That's perfectly fine. I have absolutely no problem going over some of the pieces again. So I have the game object, the empty. I dragged the cube into it. We're going to do this quite often, where we create an empty and then we put other stuff as a child of the empty. It makes creating your games a little bit easier because, for example, I could name this player right here. I could take this game object and name it player. And then if I wanted to change the graphic, for example, from a cube to a sphere, I don't have to mess with the parent object here. This might have a script attached to it or something. I don't have to mess with it, though. I could just change the cube out for a sphere. So trying to do this sort of separation where you have your sort of player game object with a graphic as a child, that can make it a little bit easier if you decide to change the graphics or you want to update some small component of it without having to change the whole game object. So you're going to see this sort of thing quite often. All right, the last thing I'm going to do is I'm going to take my mover script and I'm going to drag it from the project view here up to not the cube, but the game object. So what I should see is the transform. If I look at my game object here, I should see the transform and I should see my mover script. Now the mover script is empty. There's nothing in there. So it's not going to show anything here. But after this, we're essentially prepared for the code that we're going to end up writing. So I think on the slides, I mentioned a couple of things here. Create an empty game object, drag the script from the project view, that sort of stuff. I pointed this out here. So the game object has two components, the transform and the script. Here I've named the script hello, but our scripts can access any component in here. So my script can access the transform. That's how we're going to change the object. If I change the X position, the object will appear to move on the screen. So my script will be able to modify the transform. That's how we get things to look like they're moving. The other elements here that you see, things like the tag and the layer and some check marks and some check boxes and some drop downs. Those are all sort of other things that you can do to the game object. We'll talk about some of them later. Things specifically like the tag and the layer and stuff can help us do certain things later on. But for now, just worry about the components. So here we got transform and the hello script. All right, so we're going to do a little bit of coding. So let me go back to Unity, and I'm going to open up this mover script. And here it is. And we have our start, we have our update. Those are the two things that Unity gives us. In my class, as class variables, create a little space here. I'm going to say public float speed. I want to make a variable called speed, and I'm going to make it a float. You're going to see lots of floats in this class, so get used to seeing the number and then an F to represent the float. And let's create one more. Let's sort of assume maybe this is like a player type object. So let's say private int health. So they have some health, and maybe it's 10 or something. Whatever we want. Just based on this, you might think, all right, I've been I've been doing OOP for a while. One thing that I know, we want to follow those OOP principles: encapsulation, abstraction, inheritance, polymorphism. This, making a public variable in my class, that's not really OOP. It's not really following OOP. But you'll see this a lot in Unity. If you've never used Unity before, you might be wondering, okay, why in Unity would you necessarily do this? If you have a public variable in your script, and that script is attached to a game object, after this compiles, so we'll give it a second here, then we'll go back to the game object where the script is attached. Notice that I have a variable here, speed. The health isn't there, but the speed is. So any variables that are private will not show up in the inspector. Any variable that is public will show up in the inspector. There's ways to get private variables to show up in the inspector. And sometimes I can be a little lazy and I don't always do this, so I just make a quick public variable or something. But if we want health to show up as well, we need a little tag. And sometimes you'll see the tag on the same line. Sometimes you'll see it on the line above. Both works. You use 2 brackets, like we're doing something with an array. But we're going to say serialize field. So little brackets like this, the square brackets, and then serialize field. When you serialize a field, it shows up in the inspector, even if it's private. So it says force Unity to serialize a private field if I hover over the serialize field. So you can still make your variables private. You can still follow the sort of normal OOP guidelines. But if you don't want to deal with serialized field, if you make something public, it will show up in the inspector. So let's go make sure that's saved. Make sure that's saved. And come in here, let this compile. And there's the health. And notice it has that value of 10 that I started it with. So you have some options when it comes to these variables, but keep that in mind. Private variables won't show up unless you use serialized field. Public variables do show up. And they can be many things. It doesn't just have to be an int. You can put Booleans in. They show up as checkboxes. In fact, if we look at the cube here, these drop downs and the sort of ways to pick stuff here and the checkboxes, these are all serialized fields within the scripts that these components represent. So you can do all kinds of cool stuff just with the editor in code. I don't know how to do all of that stuff. I mean, I know how to, if you use just basic types and stuff, it will, you can create drop downs and checkboxes and stuff. But you can do some very complex stuff with the editor. So if you download a plugin or something, you download a package or something that adds something to Unity, and you see some really cool things happening in the inspector, that there's a bunch of code behind that. And I haven't messed around with a lot of that stuff. I haven't done any more than just basically some basic types and some classes and things. But there are some pretty cool stuff that you can do with things in the inspector. You can make sliders and stuff like that. For now, we're mostly going to keep it at things like variables and game objects and some other components and stuff that we allow to be public. But that's mostly up to you. The nice thing about making a variable public is that I can change it very easily in the inspector. I don't have to go back to my code, change the value in my code, come back to Unity, recompile, and run again. If I say, if I'm messing around with the speed of the movement, I can test it, stop the game from playing, change the movement, play again, see if it works. It makes it very easy to tweak things. So for variables that you might end up tweaking, like speed, like health, having them be public or at least serialized in some way is super, super useful. Okay, so let's move to a different piece here. I want to print something out. I want to get some information. So let's go in start. And let's grab the position. So I'm going to create a vector 3. And I'm just going to call it pos. You're going to see me call the position pos most of the time. And I'm going to grab the transform. The nice thing about the transform is that it's already there. Every game object has one. So in order to access a transform, you just have to do this dot transform dot position. This is a vector 3. So we're saving it into a vector 3. Notice that it is a property. It has the transform dot position get set. So it uses that property stuff that we talked about last time. So we grab this and we can print it out. So we're in a mono behavior, so I can use print. Otherwise, you can use debug.log, or you can even use, you should be able to use console.writeLine and stuff in there as well. And I'm just going to print the pos. There's nothing special I have to do. This will print it out as a vector. Think of vector 3 having a toString that sort of prints it out in a useful way. So do that, make sure it's saved. Go back. Now remember, I have to run the program to see any sort of output. I also have a warning down here in the console. It says the field mover.health is assigned, but its value is never used. So you will see some of these warnings potentially come up, especially when you use serialized variables. Sometimes you may not set them to a value initially, or you may not use them initially. So you might see some warnings pop up about that. We're just going to ignore it. And we're going to run. And what you see down here is 0, 0, 0. So I grabbed the position of not the cube, but the game object that my mover script is attached to. And its position is currently all zeros. And it tells you a little bit about what was calling it to. It says Unity engine .mono behavior .print. So that was technically what I was calling. And I sent in an object. And that object was a vector 3, which is 0, 0, 0 at this current time. So that's how I can grab my position of the object. Now, if I had other components on here, that's what we're going to do right now. We're going to add another component. So there's a button here for adding a component. You can always drag a component on. If you have another script, you can always drag it onto the object, or you can say add component, and you can start typing. There's a whole list of these things. Typically, you're not going to be clicking through this list. You'll sort of know what you want. So we're going to add a rigid body. There's a 2D version if we were using sort of 2D sprites or something that we might want, but we're just going to add a rigid body, just a straight up rigid body. Now, I'm not going to play with anything in here. We might want to turn the gravity off, but this just has information about the physical properties, the mass of this object, the drag, the angular drag. Use gravity, interpolate types of collision detection you might want to use. If you have any constraints for position and rotation. So there's a lot of information in here, and it's related to the Unity physics engine. So actually, we probably should turn the gravity off. We can keep it on so you can see it sort of start to fall as gravity affects it. But we're going to have the rigid body on here. And the point of putting the rigid body on this is so I can show you how do we access the rigid body once it's on the object. Because not every object will have a rigid body. They all have a transform. But that's it. That's all we know. That's all we know for sure that it has. So our code, we can do this because we know it has a transform. But we don't know if it has a rigid body or not. So we have a few options for this. So up here in my class variables, I'm going to create a private rigid body, and I'm going to call it just lowercase rigid body. Sometimes you might see me call like RB for rigid body, but I'm just going to do rigid body here. So I have a reference for a rigid body. That's what this is. This is a reference to a rigid body. In here, in start, I'm going to say rigid body equals get component with the angle brackets rigid body, and then this is a function call. This is how I get access to the other component. So if I have a rigid body component, I can get access to that rigid body by using get component. You put the type that you want in the angle brackets. This is basically a generic function, just like you would see in Java. And then that itself is a function call. So this gets me the rigid body, and now I can do any rigid body stuff. So maybe I want to say rigid body, my reference, dot use gravity equals false. So now I have access to that component, including all of those things you saw in the inspector. Use gravity. I can say false. It will uncheck that when the game plays. So it's checked right now in Unity. But as soon as the game plays, I get the position of the transform, I print it out, I grab the rigid body, and I turn gravity off. So if I save this, come over here. Right now in the rigid body here, you can see it had the check marks on, but as soon as I play, now the check mark is off, and the ball, the thing is not falling. So Jordan, do you not need to use get component for the transform? Correct, because every game object will have a transform. So you can think of it as just it's a default component that everybody has, so you don't have to worry about using get component. But anything else is we don't necessarily know if it has a rigid body. There are ways to force components onto objects, but you still have to use get component to grab them. So get component, you don't need it for transform, but you will need it for anything else. Now, of course, the mover script doesn't need to get a component for itself because it is itself. But if I had another script on here, if I had some secondary script or something on here that did something else, then I could use get component and grab that script as well. Yeah, so let's remove the rigid body. So remove the rigid body. The other question here, you'll get if you use get component, it can return null. If there is no rigid body, you'll get a null. So if I do that from here, I will get a null when I get this back, and then I won't be able to do this because there is no such thing as null.useGravity. So if I do this, I run. My error down here says there is no rigid body attached to the game object, but the script is trying to access it. You probably blah, blah, blah. So I'm trying to access a rigid body. There's no component attached to it. So technically, yes, it does give you a null if it can't find the object. We can force a rigid body. I don't think this piece is in the slides. I do use this a bit later on. So right above the class, so the line that's right above the actual class itself, you can say require component, open up the parentheses, and say type of, and then put whatever type you want in here. So rigid body, for instance. So what this means right here is that if I drag this script onto a game object, it must have a rigid body. Otherwise, I cannot put this script onto a game object. And that's a useful thing to do because we use a game object. I'm assuming a game object here. I'm assuming a rigid body here on my game object. So this is quite a useful thing to have if you know that there should be a rigid body on it. And you can put whatever types you want to in here. It doesn't just have to be sort of Unity specific types. You can put whatever you want. So there are times when you might want to use this for our sort of final testing stuff today. We're not going to have a rigid body on our script, but this is one of the things that you can do to force a rigid body. So let's see. So Bruce. Okay. So this runs on all objects under game object, right? So not necessarily. So okay. So it's only for this game object. It's only for this. The cube is sort of a separate thing. It's a child. So if I move the parent, so if we watch what happens over here in the scene view, if I move the parent, it's going to move all the children as well. But as of right now with my script, I actually don't have access to the cube in my mover script. I would have to say like, I'd have to get components in children and get all the children and figure out what their components are and stuff. So I actually have relatively limited capabilities right now for the script to access anything related to the cube. If I wanted the cube to do something, let's say I wanted the cube to like spin or something, I would probably add a script directly to the cube, and then the cube would spin around. Maybe it would constantly spin no matter what I was doing. I would add a script to the cube to have it constantly spin. But right now, my script's only attached to the game object. So it will move, it will sort of look like it's moving everything, but that's just because the parent is moving. And because the parent's moving, the child appears to move as well. So if I bring this back to, say, -3 in the X position of the game object, the cube still shows 0 all the way across. That's because it's a relative position. When you have a child, the position here is a relative position to the parent. So that's why it still shows 0 here, whereas this is whatever value it happens to be that I've messed around with it. All right, so right now we don't have the rigid body on there. I'm going to get rid of the require component, but this is something you can do. You will see me do this now and then on some of our stuff. But that is a way to force it if you need to. Go back to the slides and see exactly where we're at. I sort of went ahead on what the slides were showing. So we saw some of this. Let's see. We added that rigid body. Again, you use type name, whatever the type is. So rigid body was in our case equals get component, that same type, and then the parentheses. And then with that reference, you can access all of the things like use gravity and whatnot. So there was that get component. Again, you can get pretty much whatever component you want. The get component here is it's sort of part of the game object. So you would say so if you wanted to sort of write out the full thing for this, it would be like this dot game object dot get component. That should be sort of the full thing. This is kind of what you're doing, but you don't have to have this dot game object because it assumes you're talking about this dot game object when you call this from a script. So you don't actually need this. But if you wanted to be sort of explicit about exactly what was happening, we're saying this script, the game object that this script is attached to, that's what this dot game object means, dot get the component rigid body. So that's sort of what this whole thing means. But most of the time you can omit the this dot game object unless you're feeling like you want to make sure that that's in there. So again, these are some quirks of Unity. A lot of stuff you can ignore, but some stuff they are really picky about. So yeah, it's one of those engine things. All right, so we did this more or less last time, so I'm not going to bother sort of creating a couple of extra scripts, but you're not restricted to mono behaviors. We did this before. You might have some data class or something that doesn't need to be attached to a game object. And in that case, you can just create it like you normally would in something like Java. So data D equals new data, and that's fine. You can still even use the Unity engine stuff here. So you can still use, the data can contain things like vector 3s and rigid bodies and whatever you want. That's fine. It can contain game objects, references to game objects, references to whatever Unity stuff. That's fine. You're not just restricted to pure C# things when you do this. So we'll do that later on when we have our when we look at a factory method pattern. We will see that a class that we're using as a factory, which is not a mono behavior, will have references to game objects, and it will instantiate those game objects and stuff. So there'll be some cool things with that. So if you want to make regular classes to represent other things, feel free to do it. And then you can just create them sort of straight up like this. Okay, so let's do a movement example. So we already did the cube stuff here. This was a little bit later on, but we already did the cube stuff. I grabbed the cube stuff onto the game object. I'm going to clear out that script that we wrote. I don't need all the other stuff that's in there, and I just want update. I'm not going to do anything with start. We're just going to do update. We're going to clear it out, start mostly clear. We're not going to use a rigid body either. So let's go ahead and do that. So on here, we just have the script and the transform. And then on here, I'm going to get rid of start, and I'll keep speed, but I don't need the health either. So I just want update, and we'll keep the speed for the moment. Yeah. So I want to get this thing to move. And so I want to get this thing to move. And I want it to move when I press the arrow keys. Unity does have an input system that we're not going to talk about at the moment. I just want to do some simple arrow key stuff. If you made a game or something when you were in CS2 using JavaFX, this is going to sort of look similar, but in the Unity way. We'll mess around with more sort of input stuff and like input axes and stuff like that later on. In order to move something, we need to know its position. And I'm not going to use a rigid body, so we're not going to use the sort of Unity physics yet. We will use Unity physics in the future, but we're going to code with our own physics. So I'm going to create a vector 3. And really, it could probably be a vector 2 because I'm only going to do like up, down, left, right. I'm only going to do 2 dimensions, but we'll just create a vector 3. And I'm going to name it pos, just like you've seen before. And it'll be this dot transform dot position. So I'm going to grab the current position. That's a very common thing. You will see this line all over the code that we write. And then I'm going to check for an input. And remember, this happens in update. So I do this every single frame. Every single frame, I check for the position. I check and see if, and these are just some of the Unity classes that you use for this. Input dot, let's do get key. And we're going to use key code dot up arrow. Again, these are just the sort of Unity things that you'll have to remember. Obviously, if you've used other sort of libraries or game engines or something, they're probably different, but maybe somewhat close. So input is the class, get key is a static method in that class, and then key code is just key code might be an enumerator. I don't remember. Let's check. It's probably a class. Nope, it is. It is an enum. So it's an enum, and then up arrow is one of those. So if we got this key up arrow, let's change and I'm going to type this first, and then we're going to have a physics lesson. Let's say pos.y plus equals speed is the value I have up here, times time, capital T, dot delta time. Just going to look like this. We're going to talk about this. Don't worry. We're talking about sort of what this means, what this is actually doing. That's going to be part of the physics lesson. And then afterwards, I'm going to say this dot transform dot position equals pos. So we're grabbing the position, changing one of the pieces of the position, and then resetting the transform. This happens every single frame. So in principle, if I press the up arrow, it should go up. Let this compile. And I'm going to clear these out here, clear out my little messages here. And what you're going to notice is we get into play mode. We have the camera. The camera's at a different angle than our scene view. And there's a cube. And if I press the up arrow, which I'm doing right now, nothing happens. Remember, our speed was here in the inspector. So I'm going to change that speed. Let's change that speed to 5. Change that speed to 5. We'll just change the value here. Now, if I press the up arrow, it works. Now, if I press anything else, it doesn't. I didn't code anything else. But if I press the up arrow, it works. If I stop playing, notice how the speed goes back to 0 here. It sort of resets those variables. So if you change something in play mode, it gets reset to what it was before afterwards. There are options to change it so it stays whatever it was in play mode, but it lets you sort of dynamically change things in play mode if you want to. And then it goes back to whatever the default was. So you have a few options for making sure that gets saved after you exit play mode or whatever, but I typically keep it this way. So maybe that was too fast or something. I change it to 3. I come back in to play mode. Yeah, sure. That works great. Let's talk about why that works. So remember what this looks like. Pos.y plus equals speed times time dot delta time. So there's that code. So grab the current position, up arrow is pressed, change the y position, update the transform. That's all we're doing. But then that's the question. Why does this work the way we want it to? Yes, we're changing y. So we should get movement in y, or what looks like movement in y. But specifically, there's this time.delta time thing. How is this updating our position in some more or less realistic way? So speed is a constant. That's what we set. Pos.y, the y position, is what we're changing, and we're increasing it. That's why we have the plus equals. So that's why the block appears to be going up. So time.delta time, that's something that we need to think about. It's the amount of time that has passed between this frame and the previous frame. Now, that might be a very short amount of time. This is going to be a small number, on the order of like milliseconds, probably less. If you have a 60 frame per second game, your game is going to be updating, your frame rate is going to be updating at about 16 milliseconds per frame. Now, we can get some information about the frame rate here. The frame rate is probably much higher. Of course, my monitor is only displaying at 60 frames a second, but the frame rate for the game overall is probably much higher. So this is probably, a millisecond or less in the game that that we currently have. So that's going to be a small number. So 60 FPS game, it's about 16 milliseconds. What happens if we don't have it? Let's take a look. So I'm just going to comment it out. So we're just going to have the Y position plus equals speed. So let that compile. We'll run. And I'm going to press up one time. And it's gone. Notice the position. Notice the Y position over here in the inspector. It's 48. And if I keep pressing, it just gets larger and larger and larger. I press it a few more times. 594, and I could keep going. So clearly that's not what we want when we press the up arrow. Remember, it happens every frame. Every frame of this game, which is probably hundreds of frames per second that this is running at, because it's not very intensive, I'm doing this. My speed was only, like 3 or something? And yet I pressed it just for a moment, and it was up to 48. So clearly having this time.delta time is important for making some realistic looking motions. So that's where the physics lesson comes in. Because in this function, we're actually solving a differential equation. This code that I write is actually solving a differential equation. So it may not look like it, but this is what sort of got me into the sort of computational physics, sort of computational science type stuff, was when I first took a sort of a computational physics class and realized that any of those tough differential equations you might have seen in math class, you can typically solve them in just a few lines on the computer, which I always thought was really cool. Okay, so let me go back over to the slides, and let's do a physics lesson. It's probably the last thing you thought you would see today would be some physics stuff, but that is where I came from. I try to put some physics in if I can sneak it in every once in a while. So really what we're dealing with here is a position that's changing over time. Our object is moving. Right? It's a position that changes over time. So that's just dx dt, a change in position over a change in time. That's just velocity. So the velocity of my object is just how much it's changing over time. Well, you remember way back from probably Calc 1, a definition of a derivative is easy to write. Right? We just have x at the current time plus a little bit of time later minus x at the current time divided by that little change of time. So again, think of this as later, because it's the current time plus a little bit time later. This is now, and this is that, that delta t, that time later, that little bit of time that went by. So you can kind of already think of this in terms of sort of game or sort of Unity engine speak, right? This little bit of time later is what? That's the frame difference, the time between the frames. It's interesting. So we can rearrange this so that we can compute where the object is going to be in the future, right? A little bit in the future, a delta t in the future. That just equals the velocity times delta t, a little bit of time, plus where it is now. Let's go back to the code. Right here. I'm using plus equals, but really it's this. It's where I need to be in the future, so on the next frame, or sort of on this frame after the previous frame, where I am going to be in the future is equal to where I am now plus my speed times a little bit of time later. So that's all I've coded. I've coded the solution to this differential equation. A change in time, or a change in position over time is velocity. That's all I've done here. That's the equation that I'm using. So velocity, change in distance over change in time, using the definition of the derivative, rearrange it. We have the equation for figuring out where we are going to be in the future based on our speed and what our position is right now and how much time has gone by, which is for us is just time between the frames. So that equation, and I have the little pointer saying here, position dt from now, speed, effectively our velocity. We're only going in one dimension, so it's not really velocity, it's speed, but our dt, small time, and our position now, and that's it. That's the equation that we use. So that should look familiar for what we coded up. So what is time.delta time? That's dt. So where if you see like a math equation like this, or I sort of tell you, oh yeah, it's going to be something times dt, that dt is time.delta time. So we're using real physics to move our object, even though we're not using a rigid body. This is real physics. This comes straight out of your physics textbook. That's how we're coding it. So I've done things like this before with like pendulum motion and other things in some games that I've worked on, where I've just I couldn't get the rigid body stuff to work the way I wanted to, so I just went in and said, all right, I'm going to come up with some of my own physics. So Unity does have its own physics system based on a rigid body, and we will see that in the future. But at a fundamental level, this is what the Unity physics system is doing as well. They might use a little bit more sophisticated solution to this. You can do sort of higher order derivatives and get some other information about that to be able to compute to get a better approximation for this equation. This would be called if we were like solving an integral or something with this would be called the Euler's method, which is just first order. It's just first order in space, first order in space, and first order in time, if I remember right. So it's not that great of a solution, but we're not doing nuclear physics for research here. We're making a game, so it doesn't have to be 100% awesome realistic. As long as it looks good, then it should be fine, and as long as it's performant. That's one of the other things to think about. So yeah, so behind the scenes, it's just doing this. The Unity physics system is just doing stuff like this. So there was a physics lesson. Hopefully, it wasn't too traumatic. If you still need a lab science class, I would recommend physics. That's where I came from, so I'm a little bit biased. But sort of realizing how the math behind differential equations, physics equations that you end up deriving that are differential equations, and computationally how you can solve them, I think is this awesome trifecta of being able to go from that pure sort of theory math to the sort of applications in physics to being able to program up the simulation yourself, because that's effectively what we've done with this basic motion. So in any case, that's the explanation of what that equation does. So let's throw this into a few more directions. So I'm basically just going to copy and paste this little piece here and that we already wrote, and I'll paste it in a few times. And I'm going to change to like down, left, right, and change the appropriate sign and an XY position as well. So I'm going to do that right now. So I'm going to take my if, and I'm going to paste it a couple of times. And we want to have the down arrow. And we'll do left arrow and right arrow. And for down, we're going to want to, let me just do, I'm going to go back to like say minus equals. This one will be plus equals. And then for the left arrow, this will need to be the X position, and left on my screen should be minus. So say minus equals left. And then this one should be X as well, but this is going to be the plus equal for moving right. And if this is something that you forget, like, wait, which direction was left is negative, right is positive. You sort of get those flipped around. It'll be pretty easy to figure out once you run. So I think this is going to be correct, but we're about to find out. So again, it's just a matter of me throwing in those extra directions there. So it's not sort of too imperative for what we're doing. So yeah, so I'm just moving around using the left, right, up, and down key, and it's a little bit slow. I'll increase this a little bit. It's up like 10 or something, and we get it moving around a bit faster. Now our camera, we haven't done anything with the camera yet. It's on perspective mode, so this is a cube, even though it doesn't quite look like a cube here. But this is sort of your basic sort of interacting with a game object, the position in Unity using some vectors and some of the key stuff. Jeremy, I'm not actually sure. I know that certainly a lot of keyboards have those sort of capabilities. I don't know if there's something like the capability to hit a whole bunch of keys at once or in very short succession. But as far as what Unity does in those situations, I'm not actually sure. especially if you get more than one key on the same frame, or if you're holding down another key and hit one, you're holding down a key on a certain frame and you hit additional keys. I'm not sure how it would record it. That is an interesting question. I've never looked into it before. But that could be something that I look into once we start messing around with some of our input stuff. See if there's some sort of interesting, either something weird that happens, which for Unity could be quite likely, or if they have a specific way to handle that sort of stuff. All right, so there's some just basic movement using some very simple get key and some very simple physics on our position. So this wasn't a whole lot. This wasn't as much sort of C# stuff as it was Unity provides you with vector 3s and transforms and components, and you can access them, and there's just time delta time, and you're going to see a lot of that stuff. You're going to see a lot of these things where I'm going to tell you like, oh, Unity has this thing that you can do, and then boom, I'll show you sort of what it does and the classes you use with it and stuff. And that's a lot of what Unity is. It's getting used to using essentially the library. You're essentially learning the library itself, and then throwing a game on top of using the capabilities that the library has, especially when you're first learning some of this stuff. So keep in mind here that we're moving the game object. We're not actually moving the cube. We're moving that game object empty. The cube is that child. And so if we move the parent, the child moves 2, but the child is still at 0 in reference to the game object that we're actually moving. That's something that we'll come back to in the future, because we're going to make our player character will be an empty, and its graphic will be a child. And that makes it easy for us to maybe change the graphic and mess around with adding other stuff to it in sort of an easy way. Like, for example, if we had weapons that could be swapped out. Well, the weapon could just be a child of the game object. And if we want to swap the weapon out, we just remove the weapon from the game object and put a different weapon in. That way, we're not adding components to our game, or adding components to say other scripts or something. We're not adding them to our game object in real time. We're adding a child object rather than extra components. So there is some benefit to doing things like this and thinking about this sort of hierarchy that's happening. All right, so that's basically all that I have today. There's lots of functions, lots of types, lots of settings for interacting with game objects. We'll talk about some of them as we go on, but at this point, we're pretty much ready to start working on our games and just sort of seeing some of this stuff in action. Because you can spend a whole semester just doing little stupid things like this, and that's not what the class. That's not what this class is about. We're not going to spend. This isn't going to be like a CS2 class where we're doing little dumb examples a whole bunch of times and then hope that you understand how to make a big project. We're going to actually make some stuff. So our first game we're going to start next time. The starter code for that is in the repository that you have for the first PA. So I'll go over some of that stuff next time. Even though this class is all online, I will be on campus in the mornings for my CS2 classes, and then around 11 o'clock or so, that's when I will head home. So I'll still be in this setting, mostly because I don't want to try to use Unity on my my school computers, because certain aspects of Unity cause my older computer to crash. So I do want to still do it from here. So I should still be in this setting. But if anything does come up with that commute, I'll let you guys know. It should only take me about 20 minutes or so to get from campus to home. But we will be in this setting. So hopefully that doesn't impact anything. But if it does, I'll let you know. So other than that, that's all I got. So have a good weekend, and I will see you guys on Tuesday.
Thanks, Professor.
Yep.
Thank you.
Thank you.
Thank you.
Nice weekend, Professor.
Guys.